All right, let's talk about a technology that's hiding in plain sight. It uses a secret superpower of the humble electron to completely revolutionize, well, pretty much our entire digital world. Just think about this for a second. What if the most fundamental building block of our digital world, the switch, could be way smaller, way faster than anything we have now? And, this is the big one, remember if it was on or off even after you pull the plug. Sounds like sci-fi, right? Well, it's not. It's the promise of spintronics. So, to really get a handle on this incredible future, we first need to look at a property of the electron that, for the most part, we've just completely ignored in all our regular electronics. Okay, so here's the deal. For more than 100 years, everything, from your light bulb to your smartphone, has worked on one basic idea: taking the electron's charge and just pushing it through a wire. Simple. But spintronics, it's a whole different ballgame. We're not just using its charge anymore. We're grabbing hold of its other, much more mysterious property, its spin. We're going from just pushing electrons to actually controlling a quantum state. So what on earth is spin? Well, it's a fundamental quantum property of every single electron, just like its mass or its charge. And really, the easiest way to think about it is like a tiny little compass needle that's built right in. And this compass can only point in one of two directions. We just call them up or down. That's it. It's a perfect binary system, a 1 or a 0, built right into the fabric of matter itself. So we've got this amazing up or down property, which is great. But how do we take that totally random quantum behavior and make it do something useful? How do we tame it and get all those little compass needles to point the same way? Well, here's the problem. If you look at a normal electrical current, say in a copper wire, the electron spins are a complete mess. They're totally random. As you can see here, you get a perfect 50-50 mix of spin up and spin down. They all just cancel each other out, so the net spin is 0. In this state, it's completely useless for carrying any kind of information. The secret sauce, it turns out, is using a special kind of magnetic material called a ferromagnet. You know, stuff like iron or cobalt. These materials have these powerful internal magnetic fields that can actually influence the spin of any electrons that try to pass through them. And this lays it out perfectly. See, you start with that random current, just a chaotic jumble of up and down spins. Then you pass it through the ferromagnet, which acts like a sort of gatekeeper. It pretty much forces the electrons to line their spins up with its own magnetic field. And what comes out the other side? A spin-polarized current. Suddenly you have a whole stream of electrons all spinning in the same direction. We've created order out of chaos. Okay, so let's see how this builds into something really amazing. Now that we can make a current where all the spins are aligned, we have the basic tool we need to build a completely new kind of electronic component. And this component is called a spin valve. And its structure is surprisingly simple, almost elegant. It's basically a little sandwich. You've got one magnetic layer, a super thin insulating layer in the middle, and then a second magnetic layer. And that's it. That simple setup can work as an incredibly effective switch. So here's how it works. In the first state, the magnetic fields of both of those layers are pointing in the exact same direction. So when our spin-polarized current shows up, the electrons see a clear path ahead. Their spins are already lined up with both layers, so they just breeze right through. This creates a state of really low electrical resistance. That's our on switch, our binary 1. But now, look what happens if we flip the magnetic direction of that second layer. Now they're anti-parallel, pointing in opposite directions. So when our electrons pass through that first layer, they suddenly smack into the second layer and they're totally misaligned. It's like hitting a wall. This causes them to scatter and get blocked, which creates a state of very high electrical resistance. And that's our off switch, our binary 0. So this right here, this is the whole point. This chart shows the huge difference in resistance between those two states. When the layers are parallel, resistance is super low. That's a clear 1. But when they're anti-parallel, the resistance just skyrockets, a clear 0. It's this giant, easily measurable difference that makes the spin valve such a perfect and reliable switch for digital information. And this isn't just some cool physics trick you do in a lab. This ability to make a reliable, tiny little switch based on quantum spin has some incredible, tangible benefits that are already shaping the next generation of our tech. So why should you care? Well, spintronic devices are insanely fast, they're way more energy efficient, and you can pack them in much tighter for higher data density. But the real game changer, the absolute killer feature, is that they are non-volatile.
Because the state, the 1 or the 0, is stored in a magnetic direction, not a flow of electricity, it remembers where it was set even when you turn the power off. Imagine computers that turn on instantly, no booting up, or massive data centers that use a fraction of the power. That's the advantage.
And this quote really says it all. This isn't just a small step up. Learning to harness an electron's spin, it's a truly fundamental shift in how we think about and build our digital world. We've just opened up a brand new toolbox.
So we've mastered the electron's charge, and that gave us the 20th century. Now we're mastering its spin to build the 21st. And it really makes you wonder, right? What other hidden properties are just waiting for us out there in the quantum world, ready for us to discover and build the next big thing?
Thanks for watching.